trends that we see on the periodic table. So let's just start with some of these important sort of trends. Uh, One of them is the effective nuclear charge, and the effective nuclear charge is sometimes referred to as Z effective. And essentially, when we talk about sort of atoms, they obviously have electrons. And when we talk about the electrons that atoms have, they basically have two types of electrons that we usually come across. And ones are the outer electrons, and those are the valence electrons. And those outer electrons, higher in energy. And the number of valence electrons that you hopefully remember is equal to the group number on the periodic table. And then there are core electrons, which are lower energy electrons, often closer to the nucleus. And as you will know, and that's some of the trends that we'll talk about here today, it is those valence electrons, which are outermost electrons, that are involved in important things like bonding that we see, chemical reactions, and equations. Again, core electrons typically are not involved. So the idea of Z effective is uh, there are certain electrons, and typically they're the valence electrons, because of their sort of position from the nucleus, are not held as tightly as, say, those core electrons. So if we take just a very simple example like lithium, and lithium's number 3 on the periodic table, which means it does have 3 electrons. And if we write the electron configuration for lithium 1s2, 2s1, it has basically 2 electrons on the lower energy level. As you hopefully also remember when you write electron configuration, the 1, for example, here is the principal quantum number, the n number, like n is equal to 1. And it's basically the energy level. And here we do have 1 electron on the second energy level. So this, with lithium being group number 1, is its 1 valence electron. And these electrons over here, these 2, are really, for lithium, is core electrons. So if we just kind of get out sort of what's happening with lithium, lithium, because it does have the 3 protons, will have pretty much a positive 3 sort of charge in its nucleus. So this is sort of the nucleus here. It's going to have basically a positive 3 charge. And when we talk about electrons which are negatively charged, they are obviously attracted to a nucleus that has a positive charge. And one of the things that you might remember as well is when you talk about sort of electrostatic attraction, positive charge, negative charge attraction, it does increase in strength with the higher the charges. So like a +3 and a -3 are held together tighter than like a +1 and a -1. So what happens when we look at sort of our electrons in this particular case, and I'll just draw it like this just for visual purposes, not correct, obviously, but say on our first energy level, we have our core electrons here. On our second energy level, we got our valence electron hanging out there. So when we talk about the differences between sort of the attraction to the nucleus that these different electrons feel, there is sort of difference. And when we talk about these core electrons, which are sort of up front and really close to the nucleus, basically, thank you, they are basically going to feel the full brunt of that positive charge. So they're going to feel that really strong sort of positive charge in this case. They're going to be now, what happens when we kind of move out to our valence electron out here, it actually does not feel that full +3 charge of the nucleus, and that is because it experiences something known as shielding. And the valence electron in this case is shielded from the full strength of that +3 charge of the nucleus by the lower energy electrons. So lower energy electrons will actually shield positive charge that's happening to those higher energy electrons. The result of that is that outer electron, which is the valence electron, does not feel that full positive 3 hold. It actually feels something much less than that. And you could actually calculate that. And that is what is known as Z effective. And Z effective, basically, you take the positive charge in the nucleus, the number of protons, you subtract it from the number of electrons just doing shielding, which in this case is 2. So effectively, what that electron out there in the valence electron is actually feeling is more of a +1 attraction to the nucleus because of that shielding that's happening. And because of that, it's not going to be held as tightly as those core electrons. And that again is why when we talk about bonding and most things that happen in chemical reactions, it's all about the valence electrons involved in that because again, they're not held as tightly. Now, in terms of general trend, when you look on the periodic table, Z effective increases as you go to the right and up, and decreases as you go down on the periodic table. And that's what we see here on this little chart. This is sodium, magnesium, aluminum. It's basically period 3 on the periodic table there going across. And as we go from left to right, which is basically going in this direction, we do see that the effective nuclear charge increases. And the reason for that is as you move to the right, if you look at the atomic number gets larger kind of as you go to the right, which means the positive charge within the nucleus gets bigger. So what happens is it pulls everybody in because, again, it has a bigger starting positive charge in the nucleus and will also end up with a larger effective nuclear charge there as well. So that ultimately brings everybody in. And as we'll talk about, that's really important for like the size as well. That's why when we go up and to the right, things sort of get smaller because of that. Everybody gets kind of pulled in closer to each other because they do have a lot more nucleus, positive protons in the nucleus. And that's what we see here. You can again see that size decreases as you go to the right and increases as you go to the left. And that does follow sort of effective nuclear charge as well. So even the outer electrons as you go to the right are going to actually be closer to the nucleus because it's just starting with a greater positive charge within the nucleus. Now, a majority of what we are going to be talking about in this chapter is transition metals. And as I mentioned before, they are basically the heart of complex ions. They're usually the metals that are in the middle. And hopefully we remember that our transition metals here are right there, right? So these are our transition metals. And when we look at our transition metals on the periodic table, we do see a couple of things. First off, these 2 rows on the bottom, as you may also remember, if you follow the atomic numbers, actually go kind of like right about there. And those 2 on the bottom are sometimes referred to as intertransition metals because of that. They also begin on the D block, are transition metals in terms of electron configuration. As you may also remember, group 1 and 2 here, this is our S block because they could hold 2 electrons. From like group 3, 4, 5, 6, 7, and 8, that's our P block going through there. And our D block over here is right about there. And this is our F block that happens here. Remember that because the Ds do not start until the 3rd energy level, that this is 3D here and not 4D, and then 4D, 5D, and 6D coming down. The period numbers going this way is equal to the principal quantum number, basically. So that would be like n equals 1, n equals 2, n equals 3, n equals 4. So remember that D is basically 1 behind the period number. And down here, the F's don't start until 4, so that is 4F. And since it technically goes here, which is the 6th energy level, it is actually 2 behind the 6th energy level, our period in that particular case, with that being 4F, and below it would be 5F. So we will majority be talking about really kind of the main transition metals there. Not too much happening down here. More in nuclear chemistry, we'll get down into those couple rows down there. When we talk about transition metals, they do show very similar characteristics within a vertical group on the periodic table. And they tend to form ionic compounds. And one of the things, as you probably also remember from transition metals, is that they can form more than one oxidation state. And in normal naming, right, those are typically the ones that we use Roman numerals to name them, like copper 1 something, copper 2, iron 3, iron 4, whatever it may be, or iron 2, and so forth. Now, cations of sort of these ions are typically found as the metal in a complex ion. So a complex ion is typically a metal ion in the middle, has some type of positive charge, and attached to them are a bunch of these things that are known as ligands. And we have a bunch of these ligands. And the ligands are basically Lewis bases, and a reminder that Lewis bases, bless you, are things that will donate a pair of electrons. So not accept, but donate a pair of electrons. And a Lewis acid is something that will accept a pair of electrons. So a lot of times when we look at sort of complex ions, we think of it more as a Lewis acid base situation happening. And we have seen this previously, for example, when we're doing the like hydrolysis experiment, right? It's just something like this. So there's our sort of complex ion. Uh, Also complex ion happening here in this case. So in these situations, like I mentioned before, sort of a Lewis acid base. So what makes these ligands really good, for example, like water here, water is a polar molecule. It's got these non-bonding electrons on them, and that allows them to be donated and act as a very good Lewis base. Now, when you are positively charged, like a lot of our metal ions are in the middle, that means that typically you've lost electrons and you're electron deficient. And because you're electron deficient, that also makes you a really good Lewis acid because you're willing to accept electrons because you've kind of lost them. So things that are positively charged makes pretty good Lewis acids. And again, that's why our transition metals are typically found in the center of a complex ion. And here's another example. This is cobalt, which again is a transition metal. The cobalt in this particular case has a +3 charge, and it's attached to 6 of these ligands, and that's NH3. And once again, NH3, much like water, also a pretty good Lewis base because it's polar and it has those non-bonding electrons up there on the nitrogen in this particular case. Before we're done with this chapter, you will know how to name this thing properly. So, you call it something like hexamine cobalt 3 ion or something like that, and you'll be able to name it properly as well. So ionic compounds with transition metals, most of them will make some different sort of color type of solutions. And even though you may have the same transition metal that is present, depending on its oxidation state, for example, if it's an aqueous sort of solution, it may absorb light at a different wavelength and it may result in some different colors. A lot of compounds are paramagnetic, which means, again, typically have some unpaired electrons sort of happening. Diamagnetic, they sort of pair off with each other in terms of their spin. Now, electron configuration is also really important for some of the stuff we're going to talk about towards the end of this chapter. So let's just talk about that real quick here, just to remind everybody. I hope so that it's just a reminder. So remember that there are different orbitals. So there are s orbitals. There's one type, and any individual orbital could hold a maximum of 2 electrons. So since there's just one type of s orbital, it could hold 2 electrons. That's your spherical type of orbital. For p orbitals, there's 3 different types: px, py, and pz. And once again, each can hold 2 electrons, so you can max out the P, which is sometimes referred to also as a subshell or sub-level when you have multiple orbitals that are the same on the same energy level. In terms of our d orbitals, there are 5 different types of d orbitals. And if you filled each one with 2, that would give you 10 electrons maximum. And our f orbitals, there are 7 different types. And if you filled each one with 2, that would be 14 electrons. A reminder as well that on the first energy level, that is where we see s orbitals begin. On the second energy level, that is where p orbitals begin. On the third energy level, that is where d orbitals begin. And on the fourth energy level, that is where we first start to see our our f orbitals begin. There's also a specific order at which electrons go into the atom. And if you know this, basically, you could recreate that and write that for yourself pretty easily. You just go 1s and down to the right, 2p, 3d, and then 4f. And basically all you have to do is just fill in the numbers afterwards underneath each one. So 2s, 3s, 4s, 5s, 6s, 7s, then 2p, 3p, 4p, 5p, 6p, 7p, 3D, 4D, 5D, 6D, and 5F. And we always begin up on the top here, and we just keep following the arrows as we kind of go through it. We always start up here. And the main thing that people always screw up on is a reminder that when you're writing electron configuration, the S's do typically come before the D's. So when we get, especially towards the transition metals, they do fill the S's first and then the D's. So if you looked at something like iron, it would be 1s2, 2s2, 2p6, 3s2, 3p6. Again, we would go 4s2 after that, and a 3d6 happening here, as iron is 26. And if you count up the top numbers, I should have 26. So 2 and 2 and 6 is 10, 2, 6 and 2 is 20, and 6 more is 26. Also, when we write electron configuration, we oftentimes use shorthand. And if we take a look at this, that is 18 electrons. And again, if we go to the periodic table, 18 electrons is represented by argon, typically the noble gas that comes right before what you're writing. And then you do a little 4s2, 3d6 action in this particular case. So once again, when the electrons go in, it does go in, for example, here to our 4s first, and then starts to fill up. By the way, electrons do go into each orbital in the upwards direction first, right? And if there's a subshell, they fill each individual orbital up first and then come back and pair. So they do not violate Pauli's exclusion rule, which means no 2 electrons could have the same 4 quantum numbers. And we do this. Now, when we talk about transition metals, this is definitely how it goes in terms of filling. And again, you see that pattern follow over here as well. But what happens though, when we start to actually fill some of the d orbitals with electrons, there's actually a switch in energy of those orbitals. And actually the 4s becomes higher in energy than our, say, 3d in this particular case. And that's important as well for what we'll be talking about here, which is when these guys make ions. And when transition metals make ions, they always lose the s electrons first. So they always lose the s electrons first because of that switch in energy that happens. And then, if necessary, they will delve into the d orbitals, right, to take out electrons if necessary to do so. That is very different than what happens with representative metals, right? They stay and lose electrons and back up to like a noble gas. And it's usually the last electrons that you write in electron configuration are the ones that are lost. But transition metals are different. That's why transition metals can have upwards of like 12 valence electrons, as it equals the group number going through there. And right here, for example, these are irons, 8 valence electrons, the 2 S's and the 6 from the D. When we look at transition metals in terms of group number and valence electrons, we look at it much like it shows there on that periodic table on the wall. It is numbering kind of the 1 through 18 numbering. So 3, 4, 5, 6, 7, 8, 9, 10, and 11, and 12 is the number of valence electrons that those guys could have. And that's also why, for example, typically speaking, transition metals do not back up to noble gas configuration because, for example, for zinc to do that, it's got to dump out like a 12 of them, and it's probably not going to happen. And you're not going to get like a plus 12 charge sort of happening for it to fully back up. So they don't usually end up at noble gas configuration, the transition metals, because of that. Question all out there. Now, also a couple of things. There are definitely exceptions to this kind of normal filling order for electron configuration. Probably the two that most people are told they has to know is chromium, which is 24, and copper, which is 29. And again, if you wrote sort of the regular electron configuration, sort of following that zigzag arrow thing that we just made, you would end up with argon 4s2 3d4, and you would end up for copper argon 4s2 3d9. And what they've found is experimentally, they're actually more stable with an extra electron up in the d orbital and one less electron down in the s orbital. And that is the proper configuration as we see there on the screen, argon 4s1, 3d5, and for copper, argon 4s1, 3d10. Again, this could happen because they are super close to each other anyways in terms of energy, and they also do the switching, and they're very, very close in energy. So it's not very hard for sort of an electron to get promoted upwards into a higher energy level. In addition, if you're familiar with chromium and copper, you may also know that if you go to chromium and copper on the periodic table, pretty much go down and in, there is a lot more similar type of exceptions that are in that area. For example, silver is an exception, PD is an exception, a bunch of them, all in that area. For example, PD uh, doesn't even have any electrons in its S. So there's a lot more exceptions in that sort of area, although most people are told just to worry about chromium and copper. Now, again, when we lose electrons, as we've been talking about, because of the switch in energy level, we do typically lose always for transition metals the S's first, and then the D's if necessary. So earlier we looked at iron, which was argon 4s2 3d6, and iron has 26 electrons. If we had iron that had a +2 charge, because it has a +2 charge, it always has lost 2 electrons, so it would have 24 electrons. Once again, what we would do is, in terms of its electron configuration, because of that switch that occurs, it is going to be these 2 electrons that are going to be lost first here by iron, and we would end up with a configuration of argon 3d6, which means iron with a +2 charge has 6 valence electrons sort of available to it, which again will be kind of important a little bit later on this chapter. If iron went to iron 3, that would mean it has 23 electrons. Once again, it must still get rid of its kind of s electrons first. Then it will deal into this guy and take out an electron there, and we would end up with argon 3d5. And again, it d5 in this case. Question. Going to try. Let's do nickel. 2 and nickel. 4. Right, the electron configuration. Nickel is 28 on the periodic table. Okay, let's take a look. So we'll start with just nickel by itself here. So that is going to give us argon 4s2 3d8. And again, this is 10 valence electrons. If you look up there on the periodic table, nickel right above it is number 10, and that is again equal to the group number. In this case, when we go to nickel with a +2 charge, we will have not 28 but 26 electrons. Once again, it is going, excuse me, we're going to get rid of our s electrons first. So that will leave us argon 3d8 as its configuration. When we go to nickel with a +4 charge, that means it's lost 4 electrons. It should end up with 24 electrons. Again, going to take out the 2 from the S, and here we will need to take out 2 from the D, and that will leave argon 3d6 in this case. Any questions? So not there. So one of the things that you'll need to be able to do for later on this chapter is figure out how many electrons there are in an ion from a transition metal that you can then place the electrons properly. All right, let's talk about a little bit more of some of these characteristics of transition metals. These are the different oxidation states of the first row transition metals. And again, you can see there's a lot of different oxidation states, including the one we played with the other day with Mn there. And you can see a lot of different sort of oxidation states from +7 to +2. I would say a majority of them, as you kind of go through the first row, very common ones are in red. So +2s and +3s are very common. And it sort of builds to the top of Mn and then kind of comes back down as you kind of go to the middle of the row in terms of its oxidation numbers. Another really important sort of factor in terms of how things lose electrons is ionization energy. And ionization energy is the energy required to remove an electron from the ground state of an atom. We typically think about ionization energy in terms of cation formation, because obviously when you lose an electron, you become positively charged and you become a cation. Electrons, again, do not come off all at once. They actually do come off in sort of a stepwise fashion. So, for example, if we took our friend magnesium, the first thing that would happen is it would lose basically 1 electron. What is referred to as the first ionization energy, and that is the energy basically required to remove the first electron. Now, what would then happen is magnesium that has already lost an electron will go off and dump a second electron off. And that would be what is known as the second ionization energy, the energy required to remove that second electron. And then, if this process should happen to continue, magnesium would then lose a third electron here. And that would be our third ionization energy in this case. As you may imagine or may guess, it does get harder and harder to remove an electron after you've already removed some electrons. Because what happens to the size of the atom when you remove an electron? It shrinks, right? Because you lose some of that electron cloud, so the size of a cation is smaller than its neutral guy. So that also moves those outside electrons in closer to the nucleus. And now, because it is closer to the nucleus, it is going to be held tighter and it's going to be harder to remove. If you pop off the second one, again, it gets smaller, it gets harder to remove, and it just gets progressively harder and harder to remove. So the general trend that we see in terms of first ionization energy to second to third and fourth is ionization energy increases as you continue to remove electrons. So the first ionization energy is typically smaller than the second, which is smaller than the third, and so forth. The general trend for first ionization energy, when you look at the periodic table, it increases first ionization energy as you go up and to the right and decreases as you go down. And that's what we can kind of see here as well. If we look at these guys right here. This is going across period number 3 on the periodic table. And as you go across period number 3, you can see an increase in the first ionization energy. Again, 493 for sodium down to or up to 1527 there for argon. The other thing that we see again is we do see the increase between first ionization energy to second to third. If we take a look at magnesium, first one to pull off that electron in about 735, pretty much doubles almost. If you want to remove the second electron, getting harder to do. And as you can see, if you jump from the second to the third, now it's gone up by 5 to 6 sort of times, probably about 5 times or so. And it gets much, much harder to do so. And that's because when you look at the electron configuration for something like magnesium, 1s2, 2s2, 2p6, 3s2, magnesium is group number 2 and has only 2 valence electrons. The rest are core electrons. And after you remove those 2 electrons that are valence, getting harder and harder to do so, it now gets extremely hard to try to rip apart that electron that's a core electron, which was close to the nucleus to begin with. You can see energy-wise, it's not really effective to do so. That's also why magnesium, as we know, basically does a +2 charge and lays up, because at that point, any more is into its core electrons and it's not energy efficient to do so. That's also why something like aluminum, right, will stop at a +3 charge, because to remove the first one, 580, not too bad, kind of doubling or so of it there to 1800. Again, getting harder to do, up to 2700 on the third one. And then from the third one to the fourth electron, it is a giant jump there. We're up to 11,000, which again is not probably going to happen under normal conditions. And again, why something like aluminum will stop at the +3. Again, basically removing the valence electrons, as that is the easier of the electrons to remove. And again, much, much harder to remove those core electrons. Any questions on that there? Here are a bunch of stuff about the first row transition metals, some of which we've talked about, but again, obviously atomic numbers increasing as you go left to right up there, so kind of increasing going this way. Electron configuration we talked about with our couple of sort of exceptions in this first row. And again, there are multiple exceptions as well. Because of effective nuclear charge and some other things, again, we do see atomic size start to decrease as you go to the right. Here's our ionization energy, and again, gets larger as you go from first to second to third, and overall increases as you go up and to the right. Our reduction potential there coming across, and our common oxidation states +2 and +3 going through there. Density also increases a little bit as you go across. And that's another sort of trend. Here's again our third ionization energy versus our first, so a lot more energy needed to do that and remove it. Here's another one of the first, second, and third, in case you didn't like the first one. We could look at this one here, which is our graph. The next sort of trend we're going to talk about is electron affinity. To remind ourselves, electron affinity is the energy change that occurs when when an atom gains an electron. And typically, if you have an affinity for something, you like that or you're good at it. And if you have high electron affinity, you're probably pretty good at gaining electrons. So you typically will see a pretty good negative energy change that occurs. The general trend on electron affinity is when you look at the periodic table, it does increase as you go up and to the right and decrease as you go down and to the left. Electron affinity. Not a perfect trend, so you can see here. As we're talking about there again, electron affinity is typically associated with anion formation, right? Because again, if you're able to gain electrons, you're going to become negatively charged, and that's pretty much your definition of anion. Electron affinity should also not be confused with everybody's other favorite E sort of guy, electronegativity, right? And that is the ability of an atom to bring electrons towards itself also kind of has the same trend, increases as you go up to the right and decreases as you go down, with our friend fluorine, right, being the most electronegative you could have in this situation. All right, this is our standard reducing ability of our first row. And again, greater reducing ability coming to up this way. Greater reducing ability means that it will be oxidized. And we do see our positive 2.08 here voltage. And you may be saying to yourself, but shouldn't the more positive guy be reduced? When you look at each of these are actually written as oxidation reactions. These are not SRPs. These are like standard oxidation potential in this case. As if we flipped all these around to make them like SRPs, we would then change the sign of each of these, right? Make that positive if we made these all SRPs. And now here we have our one that is greater ability to be reduced is down at the bottom, and our greater ability there to be oxidized makes more sense up on top because these were reversed. There's our atomic radii again getting smaller, and one of those things are all these sort of trends that we talked about. Just go here, maybe let me something. Not through here. So if we take a look at all those trends on the periodic table that we kind of reviewed here, again, in terms of Z effective, it increases as you go up and to the right, decreases as you go down. Our ionization energy increases as you go up and to the right, decreases as you go down. Our electron affinity increases as you go up to the right, decreases as you go down. Our electronegativity increases as you go up, decreases as you go down. So that's the our size decreases as you go up and to the right and increases as you go down here to the left. And what all these trends basically tell us is when we go, for example, upper right of the periodic table, we have things that like to hang on to their electrons, like to gain other people's electrons. Takes a lot of energy to remove their electrons. They're very small and they have a bigger effective nuclear charge, which means they're going to hold the outer electrons tighter to each other. These are all things that like to basically gain electrons. And that's what we think about when we talk about nonmetals, which are found up here on the upper right-hand side. As we go kind of left bottom of the periodic table in our more metal area, we have all those things where they have very low ionization energy, which means they're not going to look to hang on to their electrons very hard. They have very low electronegativity. They're not looking to gain electrons. And they have low electron affinity because they are not looking to gain those electrons, so they're not bringing any electrons towards each other. They're also much larger because they have more electrons kind of spread out over more energy levels, and that causes them to be held a lot less with their smaller Z effective. And these are all things that typically will lose electrons and become positively charged, while nonmetals are typically things that will become negatively charged. That is also why, because of these trends, that when you put both of those things together, a metal and a non-metal, you make an ionic compound, right, where we get a transfer of electrons. That's also why that when we put two non-metals together, like in covalent bonding, we actually get sharing of electrons that happen because both of them both want to hang on to their electrons. Neither one really wants to get rid of their electron. So the best they can agree upon is sharing. Any questions on any of these trends? Uh, in case you need to pick these guys out, that is what they look like, including our pennies that they don't make anymore, I think, right? On the bottom right there. This you don't have to worry too much about anymore. But again, these are just illustrating the different oxidation states of these metals. And again, you can see it does result in different aqueous sort of solutions and complex ion sort of colors that you get. I can see there chromium, a lot of blues and greens come out, and manganese, which you dealt with the other day, browns, purples, reds happen, and iron as well here. Get some different stuff in copper. All right. Now that we sort of reviewed, hopefully, a lot of the sort of periodic trends and about transition metals, let's talk about really the main part of this sort of chapter, and that really is coordination compounds. And coordination compounds are basically composed of two things. They're composed of a complex ion, which, as we've been talking about, is a metal ion in the middle that has a bunch of these ligands attached. And it is also made up of what is known as a counter ion. So it's basically made up of those two things. We have a counter ion and a complex ion. As we will see and as we will talk about, your counter ion could be positive, and you could have a negative complex ion. Or your other option is you could have a complex ion that is positive and a counter ion that is negative. So you could think of it, as I mentioned a second ago, counter coordination compounds as really like an ionic compound. And much like an ionic compound, when we name it and when we write the formulas, it's always the positive guy first and then the negative. And that's how basically these coordination compounds work. And in this case, like I said, you could have either a positive or negative complex ion or a positive or negative counter ion. Now, as we also talked about, the ligands that are attached to the complex ion part are basically referred to as Lewis bases, and those are again things that can donate a pair of electrons. And as I said earlier, and we talked about, I think, in the previous chapter as well, things that are typically able to be really good Lewis bases and donate electrons are things that are polar, that have some non-bonding electrons. Unlike an electronegative atom like nitrogen, oxygen, which is what we see here. Also, anions, which are negatively charged, are really good because in order for them to be negatively charged, they had to gain electrons, which means they should have some electrons to give because they gained some electrons. So things with negative charges, things that have some non-bonding electrons that are in a polar molecule on some of those electronegative atoms are really good sort of ligands. Now, when we talk about complex ions, we also talk about, again, what is referred to as the coordination number. And we might have touched upon it in a previous chapter. But the coordination number is basically related to how many atoms are directly attached to the metal in the complex ion. So when we look at something like water, for example, it will only attach to the metal through the oxygen here, is basically how it's going to attach. Or the NH3 will only attach to the metal through the nitrogen here. And that means in each of these cases, we basically get a 1-for-1 in terms of ligands and the coordination numbers. So if we take a peek at that picture that was on the previous slide here, when we look at this complex ion here, which is in the middle, directly attaches cobalt is this nitrogen off of this NH3. It is this nitrogen off of this NH3. It is this nitrogen. It is this nitrogen. And now each of these chlorides are also basically given those electrons. So when we look at it in terms of its coordination number, it has one nitrogen, two nitrogens, a Cl, another nitrogen, and another nitrogen. That is going to give this guy a coordination number of 6. This happens to also be how many ligands are attached in this case. There's 6 total ligands. And in this case, the coordination number and the number of ligands will be the same. So if you had you know, this guy kind of written, it would look something like this, probably. Cl2, right? And this is sort of the complex ion part. And typically, complex ions are a lot of times in formulas put in brackets. So a lot of times, if you see like a bracket and something written in there in a coordination compound, that's the complex ion part typically of it. And if you look at it, there's obviously 2 and 4, which tells you 6, and that is a coordination number. Now, that is only because in this case, it is the same as the number of ligands attached, because those ligands, water and ammonia, are what are referred to as being monodentate, or sometimes people call it unidentate. And that basically means that in water or NH3, as I just mentioned, there's just one atom that's going to attach to the metal. So only one individual atom will attach to the metal. Now, not all ligands are like that. There are ligands that can attach in multiple places. Couple of common ones, ethyl endyl diamine. This is abbreviated in coordination chemistry with the EN. And they oddly, a lot of times will use the EN both in the name and also the formula. So people just don't want to write that big word out. So they'll kind of use it both in the name and the formula as well. And if you drew out EN, for example, give it the old college try here, see how I do. It'll look something like that, and that is ethyl endyl diamine. The ethyl means, for example, there's 2 carbons in the middle. That's based off of ethane. The di means there's 2, and the amine is this group right here. This is the amine group in organic chemistry. So that is where the name comes from. And because it has 2 of those amine groups, those nitrogens, when you have the little metal ion, it is able to attach at both of those nitrogens to the metal ion. So you get kind of a 2-for-1 deal on that. So for every molecule of ethyl endyl diamine you have, you actually get 2 atoms binding. So if you had another one down here, you would get another couple of attachments. Now, if you had this in the formula, and I'll just write metal here, and then we'll have En to the 2. And you may look at it and go, oh, I think the coordination number should be 2 because the little subscript there says 2. And it would be incorrect in this case because this is not monodentate, but bidentate. We actually get 1, 2, 3, and 4 nitrogens that are directly attached to that metal ion. And that would make the coordination number here 4 in this case. So there definitely are some ligands that can attach more than one place per molecule, and that affects the coordination number. And like I said, it's a very common error people make. They just kind of see like all the ligands, a little subscript, and go, cool, that's got to be also the coordination number. And it is in monodentate, but something like this, it is not. The other most common, probably bidentate one you'll come across is C2O42 minus. That is oxalate. And if you draw up oxalate, it looks something like this. And in the case of oxalate, actually have the 2 oxygens that are single bonded with negative charges. That is where each of those combine to a metal. So same idea. You get basically a 2-for-1 deal there on the bonding. There are some that combine in 2 places. There are some that combine in 3. There are some that combine in like 6 different places along the way. EDTA, ethyl diamine tetraacetic acid, also is one that combined in like 6 different places. So it could really grab up a metal and surround it and trap it really well because it's basically binding in many, many places. For example, if you ever look at ingredients on certain things, you'll sometimes see EDTA listed, and a lot of times they're used to kind of grab up some metals and stuff like that and keep it sort of sequestered in this particular case. So when we talk about coordination number, it is important to know whether or not the ligands that are attached are monodentate, bidentate, or polydentate as to basically how many sort of atoms you can get to bind per molecule. Any questions on that? Now, how many do we typically get in terms of ligands to attach to the metal? It is sort of dependent on the charge of the metal that's in the middle of the complex ion. And as you might imagine, the higher the positive charge, the more electron deficient it is, and the more ability it has to accept more ligands with electrons giving them to them. The smaller the positive charge, it might not have as much room to accept electrons coming in. And typically speaking, if you got things with kind of a +1 charge, common sort of coordination numbers are 2 and 4. If you get into kind of the +2 area, now you're getting into common of like 4 and 6 ligands having the ability to get in there. +3, now you can have really 6, except for gold, which is going to have 4 sort of ligands that can attach in there. So it does sort of depend on the situation of what the metal is and the ligands coming in. But again, usually the general trend is the bigger the positive charge on the metal, the more ligands it can actually accept in and accept those electrons coming in. There's our ethylendyl diamine, and this is our EDTA over here. And as I mentioned before, this thing can bond in lots of places. So it can bond one spot there, 2, 3, 4, 5, and 6. So one EDTA molecule, like I said, can really grab up a metal really well. And even this guy, obviously, a couple of these guys are going to do a pretty good job as well. And that's why they're sometimes referred to as chelating agents, because again, they really can surround those metals pretty strongly. Here's a table, and you have similar table in your book, some common monodentate, unidentate ones. Again, in terms of monodentate, water, ammonia, cyanide, nitrite, thiocyanate, like we saw there with our K equilibrium experiment, right? That's that guy right there. All of our halogens as well. There's our oxalate and our ethylendyl diamine. Here's one, as I mentioned before, here's one that could actually do it in 3 spots. And this is diethyl triamine. And triamine means it's basically got 3 of those nitrogen groups. And at each of those amine groups, basically, it has the ability to bind to the metal. So you get kind of a 3-for-1 in this situation on this guy. And then as you can see down here is our EDTA. And once again, where all those arrows are is places where they can bind into the metal. Also, all those single bonded oxygens have a -1 charge for a -4 charge overall. All right. So let's also talk about why don't we give this a go? What is the oxidation numbers of the metals? So in each of these cases, we're looking for what is the oxidation number of the metals in the complex ion. So as I mentioned before, typically speaking, when you look at a coordination compound, like we see in these formulas, when you have something that's in brackets, that is usually, again, the complex ion part. So for the ones that are in brackets, the metal that's in the bracket, which is part of the complex ion, take a moment here and for each of them decide what is the oxidation number or state for the gold and the chromium in this case. All right, let's take a look. So once again, we'll start here with this one. And as I mentioned a second ago, again, typically in the bracket part is our complex ion. And that would mean by default here, this is going to be our counter ion in this particular case. And we basically could kind of just go through it like we're assigning sort of oxidation numbers like we've done before. So for example, here, obviously we would leave the metal in the complex ion for the end. Hydroxide is -1, and there's 4 of them. That's like a -4 happening. On the outside there, that is potassium, which is group number 1 on the periodic table. So it should have its normal sort of +1 charge or oxidation state. Obviously, this is a coordination compound, so the overall charge of it is 0. So everything needs to add up to 0 in this case. So we basically got -4 and +1, which is -3. That means here the oxidation state of our gold should be +3 in this particular case. Questions on that one there. Taking a look at the next one here. This is CrNH3 6 and a little NO3 in this case. In this particular case, in the bracket is this guy, which means that this should be my complex ion. This by default then would be our counter ions in this case. And again, we're just going to kind of roll through it like we did previously. So in this particular case, NH3 is 0. Again, remember that's not NH4, which is +1. This NH3 here is 0. Nitrate, NO3, is a polyatomic ion, which is normally -1. And there are 3 of them. So that's a -3 charge. Once again, here our coordination compound is no charge. And that would mean in this particular case, our chromium would be rolling a +3 charge as well. First off, any questions on that there? So in this particular case, we do see a couple of things. If we were going to take just the complex ion part here by itself, we have figured out obviously that this is -1 and there's 4 of them. It gives you -4. We figured out that the gold here is +3. So the charge on my complex ion part is +3 and -4 is a -1 overall. So in this particular case, my complex ion has a -1 overall charge, and it is a negative complex ion in this case. That is why when I look at the original formula here, I have my friend potassium, and I only have 1 of them because potassium is group 1, and that is a +1 to balance out my -1 charge of my complex ion. So in this case, I just need 1 potassium to balance out the charge for my coordination compound. Any questions on that there? If I take a look at the one on the right here and just the complex ion part, we got chromium NH3 6. Once again, the NH3 is 0. And we figured out that the chromium is +3 in this case. That means in this particular case, my complex ion is actually positive in this case and is a positive complex ion. That is why when I come over here to my friend nitrate, which is NO3 minus, I don't just need 1 of them. I don't need 2 of them, but I need 3 of them to give me my -3 charge here. That's going to balance out the +3 charge over here, which once again is, why I need 3 of them. So in this case, we do see a positive complex ion, and in this case, a negative counter ion to balance it out. Any question on that there? Now, I could have known right out of the gate that this guy here and this guy here, they were going to be positive because, frankly, they come first in the formula. So because they come first in the formula, they should always be the positive thing, as we talked about in a coordination compound. Positive guys should come first, and the negative guys should come second. And if I see my complex ion part there and my counter ion there coming second in the formula, I know that they're going to end up being negatively charged because they come second. So you may have to still obviously figure out what the charge is if you need to know what the charge is, but you can know by sort of the placement in the formula for a coordination compound The positive guys should always come first, and the negative guys should come second. Any questions up there? All right. Then let's talk a little about here some of the rules just to finish up on to naming coordination compounds. And I know you thought maybe like naming was over, but it is almost. So to name these coordination compounds, as I've been mentioning, both again in formula and also when you name it, just like a normal ionic compound, we're going to go positive guy first, followed by negative. So again, that's always sort of the order at which things should go. Now, within a complex ion, you're going to have several ligands that are attached to the metal. And within that, the ligands are named in alphabetical order. Now, they are named in alphabetical order regardless of the prefix. So if you happen to have three of the same ligand in a compound, you may use the prefix tri because you have three of them. You don't look at the prefix in terms of alphabetical order. You look actually at the letter of the ligand as the alphabetical order. Now, some of the names of the negative ligands will end in letter O. Some neutral ones are just called what they are normally called, but really a majority of them have some funky name sort of attached to them. So, for example, things like water is aqua. Some people will call it aqua, depending on the book as well. CO is carbonyl. NH3 is amine. If there are several ligands, as I mentioned before, within the complex ion part, we do use the prefix and again, several of the same ligands. So di for 2, tri for 3, tetra for 4, penta for 5, and hexa for 6. Now, if by some chance your ligand already has one of those prefixes in its name, you do not use di, tri, tetra. You use bis, which is for 2, tris, which is for 3, and tetrakis, could be making this up, is for 4 in this particular case. And what is an example of like a ligand that may have a prefix in it? It's actually that one we saw earlier, for example, is an example en. That is ethyl endyl diamine. So since the name of that ligand has the di prefix in it, we would not use di if we had two of them. We would use bis if we had two of them. That one that had the triamine that bonded in 3 places, that also has, again, a prefix in the actual name of the ligand, so you would not use the normal prefix. I will say that sometimes people will use for oxalate the bis, tris, and tetrakis if there's more than one. So sometimes people will use those kind of guys for also ones that are maybe polydentate combined in multiple places, but oxalate sometimes used that way as well. The number of the metal is written in a Roman numeral, and it follows the metal name. So when you're naming the complex ion part, so as we just saw there, you could have a counter ion followed by a complex ion. When you're naming the complex ion part of the name, the metal should always come at the end of the complex ion part of the name. Not necessarily always the end of the name itself, but it should be at the complex ion part of your naming. It should always come at the end of it. We should also always use a Roman numeral, even for things where we normally do not use a Roman numeral, like silver. We usually don't use Roman numerals for it because it has a fixed charge, but here we do use a Roman numeral with it, like you would put 1, or zinc or cadmium, where we again typically would not use a Roman numeral because they have sort of those fixed charges. We do use them here in this situation. Also, a really weird situation that happens as well is it is possible that you will end up with a metal that is neutral. And with a metal that is neutral, you'll actually use not really a Roman numeral, I guess, but you'll put a 0 in the parentheses rather than just leaving it without something. So we always sort of use the parentheses here in a Roman numeral to indicate the charge on the metal that's within the complex ion. And again, even if it's 0, we actually will put the 0 a lot of times in the parentheses. The last kind of funky thing with the naming of these is if the complex ion part is positively charged, then you could roll with the regular name of the metal, like chromium, copper, iron. If the complex ion part is negative, Then we actually roll with a little bit of like the old school name of those things, metals that end in ATE. So instead of iron, it's ferrate. Instead of copper, it's cuprate. Instead of zinc, it's zincate, and so forth. And that is why earlier, when we took a look at these two, for example, it is important to recognize whether or not your complex ion is negative or positive, as that will determine how you would give the name for the metal that's in both of those things. So for this guy, because it's a positive complex ion, when we go to name the metal part here, we would just use chromium. This guy over here, we would not use gold. We would use rate, which is the gold kind of old school name, rather than gold in this case because complex ion is negative. So if the complex ion part of your guy is negative, you kind of got to roll old school with the ATE ending. Any questions on that there? And we'll see some here in the notes and just, yeah. Well, next time. All right, we will lay it up there.